Hello, today we are presenting a project on guardrail for hallucination detection and prevention. The goal of this project is to build a safe and reliable drug information assistant that minimizes hallucinations by combining retrieval based methods with a strong verification layer. About a system, LLMs often generate responses that appear confident but are not factually correct. This issue becomes especially critical in healthcare applications, where incorrect drug related information can lead to serious consequences. To address this problem, we designed a guardrail enabled system that ensures responses are grounded in reliable data before being shown to the user. The objective of our system is to build a drug information chatbot that retrieves the knowledge from a trusted drug bank dataset, verifies whether the generated answer is supported by evidence, and filters responses based on their reliability. The system assigns confidence through grounding checks and ensures that only safe and supported responses are delivered, while unsupported ones are blocked. Our system consists of several key components working together. First, BM25 retrieval is used to fetch the most relevant drug related information from the dataset. Then the LLM generates a structured JSON response. This output is validated using a schema to ensure correctness. After that, grounding and coverage scores are computed to check whether the response aligns with the retrieved evidence. Finally, a self-correcting controller helps improve responses that initially fail these checks. We evaluate four configurations for our system to understand how safety improves at each stage. The baseline model has no retrieval or verification. The RAG model introduces retrieval but does not verify responses. The guarded RAG model adds grounding and coverage checks to validate outputs. Finally, the self-correcting model includes a retry mechanism that improves weak responses. This progression clearly shows that retrieval alone is not enough and verification is essential for ensuring safe outputs. So the model comparison table highlights how each configuration differs in terms of retrieval and verification. Both baseline and the models only ensure structured outputs without enforcing correctness. Guarded RAG introduces grounding and coverage checks, which significantly improve reliability. The self correcting model further enhances performance by retrying failed responses using improved queries and stricter prompts. This layered approach demonstrates how adding verification improves system safety step by step. Our key innovation is the self correcting mechanism. When a generated response fails grounding or coverage checks, the system automatically retries using an expanded query and a stricter prompt. The response is then re-evaluated before making a final decision. Despite this additional step, the system maintains a simple binary output, either allowing the response or blocking it. This approach reduces unnecessary blocking while still maintaining high safety standards. Instead of relying on traditional accuracy metrics, we evaluate a system using safety focused metrics. These include allow versus block rates, grounding failure rates, precision, recall, and F1 scores, as well as FAR and FRR. We also analyze confusion metrics, ROC curves, and latency metrics. It is important to note that we use proxy labels for evaluation, which means the results are primarily used for comparing different configurations rather than representing absolute correctness. The results show clear differences between the configurations. Both baseline and the RAG model allow 100% of responses, indicating that they do not enforce safety. In contrast, the guarded RAG model introduces meaningful blocking, ejecting about 25.8% of responses due to insufficient grounding. The self correcting model improves upon this by reducing failure rates and allowing more valid responses. However, this improvement comes with increased latency due to retry mechanism. Overall, the results demonstrate that guardrails actively prevent unsafe outputs rather than relying on model confidence. The analytics visualizations provide deeper insights into system performance. The ROC curve helps identify the optimal threshold for grounding, balancing false positives and false negatives. The latency distribution shows how response time vary across different configurations. Additionally, the grounding score distribution illustrates how confidently the system aligns responses with evidence, helping us better understand model behavior. The evaluation visuals include a confusion matrix and latency comparison. The confusion matrix shows how accurately the system distinguishes between safe and unsafe responses. The latency chart highlights the trade off between performance and safety, while the self correcting model improves reliability. It also introduces higher latency compared to other configurations. For future work, there are several opportunities for improvement in this system. In the future, we plan to use real clinical labels instead of proxy labels to improve evaluation accuracy. We also aim to test the system on larger and more diverse datasets. Additionally, we will work on optimizing latency for the self correcting mechanism and extending the system to support multi turn conversational scenarios. This slide shows a demonstration of our system in action. We have provided the demo link in this slide. That's it from us. Thank you.